This is my Calculus 1 course. Today we're going to continue to learn how to find volumes of solids of revolution. If you haven't done the homework completely and correctly from last class, do that homework before watching this video. Get a picture of the differentiation formulas if you don't have those memorized. We're going to be using the disk method and the washer method as we did in the previous class, so get a picture of those if you need to. So in the previous class, we learned how to find the volume of solids that were produced by rotating an enclosed area about the x-axis. But today we're going to do the same thing, but we're going to rotate about a line other than the x-axis. So we're rotating about lines other than the x-axis, and we're going to start with a problem that uses the disk method. So it says here, find the volume of the solid generated by rotating the area bounded by x equals 1, x equals -1, y equals 2 to the x, and blah blah blah. And we're going to rotate about the line y equals 3. So again, usually we rotate about the x-axis, but in this problem we're rotating about the line y equals 3. That's different. It's still a horizontal line like the x-axis, but it's in a different position. So you can see that orange line is y equals 3. And so here we have the area bounded by those the graphs of those equations. And we're going to rotate about that orange line. Now again, normally what we would do is we'd rotate about this blue x-axis, but now we're rotating about a different line. And what's going to make this different is that we have to put a little more thought into calculating the radius of each disk. Now you can see we have a cup shape when we rotate that area about the line y equals 3. So let's find the volume and we'll see what happens. So again, this is the disk method. So the formula for a disk is this formula here. Each cross section is a disk with an infinitely small volume. We think of it that way, or an infinitely small width. But the cross section is really just a two-dimensional figure. It's a circle. So we're finding the area of that circle. And maybe we should write this as a of x, cross-sectional area of the solid, and then we're going to find pi r squared. So that's the formula. And we are going from x equals -1 to x equals 1. Those are the limits of integration. So let's think about this. What is the cross section? Well, it's a circle like this green circle here. And we're going to have a bunch of those cross sections. And so what is the radius of each circle? The radius is the distance from here to here, that green length. But what is that? Well, obviously the green length is going to change based on where you are, but what exactly is that green length? This is something that can cause confusion for students. It takes some getting used to, but that length is actually going to be 3, which is this distance here. It's going to be 3 minus this orange distance here. So the green distance minus the orange distance is the pink distance. We want the pink distance. That's the radius of each disk. But we're going to have to take the green distance, which is 3, and then subtract the orange distance, and the orange distance is the value of the y value of that red function. That red function is 2 to the x. So the orange distance is 2 to the x. This, believe it or not, is the radius of each disk. 3 minus 2 to the x. So you can see that this takes more thought. Students tend to get really confused by this. So if you find throughout this class that you're kind of confused about what expression represents the radius of a disk, or the inner disk or outer disk of the washer method, then that's normal. So r is going to be 3 minus 2 to the x. And of course we need to square r, so it's 3 minus 2 to the x squared. And so why don't you look over that and see if that makes sense. Again, this takes more thought. So you can look that over, and let's go ahead and calculate. So I'm going to take pi out of the integral. Remember, we have that rule that tells us we can do that. And then I'm going to expand this expression using FOIL. So 3 times 3 is 9. 3 times negative 2x is 3 times negative 3 times 2 to the x. And then we have another one of those terms. And then negative 2 to the x times negative 2 to the x. So again, we just FOILed that stuff out, and I need a, well, I guess I can just write a positive, because we know a negative times a negative is a positive, right? Okay, so we have 9 minus 6 times 2 to the x, because these are like terms, we can combine them. Now we can add these exponents, so we have 2 to the 2x. And I think I'm going to have to erase this stuff because I'm not going to have enough room. I'll move this over a little bit. Sorry, that's my, well, it's not the computer, it's the OneNote program doing weird stuff. Okay, so now we're going to find the antiderivatives. We have 2 to the x over natural log 2. Because remember, when we find the derivative of 2 to the x, it's 2 to the x times natural log 2. So we need the natural log 2 in the denominator to cancel out the natural log 2 when it pops out. Now, this is technically a u substitution, but it's such an easy u substitution that we don't really need to show the steps of that. But just be aware that technically you would make u equal to 2x. So we're going to need 1/2 2 to the 2x. Actually, we're going to need a natural log 2. So 2 to the 2x over 2 times natural log 2. So the reason that we need this green 2 is because the chain will make a 2 pop out. So this is from -1 to 1. And we may need some room on the other page here. So let's double check, make sure that's all right. Everything looks correct. Okay, so now we're going to plug in 1. to subtract the same expression with -1 plugged in. When we subtract the expression, the signs change. And so now I'm going to bring this expression up. And let's double check to make sure we did all that correctly. Everything looks correct, but you want to be very careful that we wrote all that correctly, or else you're going to waste a lot of time. So we can simplify. And we have 3 over natural log 2. This goes down. You have 6 divided by 2 is 3. We have 2 to the negative 2 power becomes 1 over 2 to the positive 2 power. 2 to the 2 power is 4. 4 times 2 is 8. So we have 1 over 8 natural log 2. So I'm going through this kind of quickly because I don't want to bore you with a lot of math here. 2 to the 2 power is 4, divided by 2 is 2. So we're reducing. 9 plus 9 is 18. Combine these, you get negative 10 over natural log 2. Plus this is negative 7 over natural log 2. Okay, so at this point you can probably just use your calculator. I'm going to combine these, get a common denominator. The most important thing is that you demonstrate that you can use the fundamental theorem of calculus with all this. So I multiply both sides of this fraction by 8. And so it looks like we get 18 minus 57 over 8 natural log 2. So at this point we can use our calculators to find an approximate answer. You could write the exact answer, but I'm just going to use a calculator. And we get 24.2 roughly. $24.2556. Okay, so a lot of busy math there, and unfortunately these problems just have a lot of math involved. But the most important thing is that you know how to set up the problem correctly. So let's do another one. It says find the volume of the solid generated by rotating the area bounded by these the graphs of these equations about the line y equals -2. So what's different about this is we're rotating about the line y equals -2 as opposed to the x-axis, which is y equals 0. So here we have, and by the way, this is going to be an example of the washer method. We have area enclosed by those graphs, and then we're going to rotate about the line y equals -2. And this is what our area looks like when we do that. So it's kind of a big a big bowl with a hole in the middle. So you can look over that if you want. Make sure you understand how we did that. And let's find the volume. We're going to use the washer method. So we're going to find the integral from 1 to 2. Looks like that's going to be our limits of integration. And it's going to be pi r1 squared minus pi times r2 squared. And maybe I'll just write that as the general formula there. So again, we're going from 1 to 2, and let's think about this. Now again, this is where things can get confusing, so you have to stop and really think about things. And it's not easy for students. So we have washers. So washers are going to be developed by subtracting a smaller disk from a bigger disk. So we're going to calculate the area of this bigger disk. You see that bigger pink disk? There's all kinds of disks as we move along here. But we're going to calculate the area of that cross-sectional circle there. Technically, cross-section area is not, it's not the area of a disk, it's just the area of a circle. And then we're going to subtract the area in the inside, and that's going to give us the area of a flat washer. Now the good news is that this circle here doesn't really change. Its radius doesn't change. So we can see that the radius of this circle is just 2, right? And that's pretty simple. But the radius of the outer disks, those radii change. So the radius of the outer disk is this length from here to here. So what we have to do is we have to take this length, which we know is 2, and then we add this length. That length is the y value of the red graph. All right, so it's going to be 2 plus, and the y value of the red graph is all the y values are represented by x squared. We have to square that because the radius is squared, pi r squared. So again, that's not something that is exactly easy to understand for students. So you want to look at that for a while, try to absorb that. Again, we have this pink distance, 2, and then we're going to add this pink distance, which is x squared. And that's the radius of the bigger disks. But then we're going to subtract the area of the smaller disks, and the radius of the smaller disk, well, that's just 2. So there you go. This integral represents, or it's going to give us the volume of this solid. It's like a cup shape with or a bowl shape with a hole in the middle of it, I guess you could call it. Except the bowl is not really concave. Okay, so now we're going to pull pi out, and we're going to expand. So that's going to be 4 plus 4x squared plus x to the 4th power minus 4. So I did FOIL and added the inner terms together. And lucky for us, those 4's cancel out. So we're left with 4x squared plus x to the 4th and now we're going to find the antiderivatives. So we have 4/3 x cubed plus 1/5 x to the 5th from 1 to 2. And maybe I'll bring this down a little bit. Actually, I've got plenty of room up here, so I guess I can just move up here. So there's always a lot of busy work involved with these problems, unfortunately. That's just something you have to do, and it'll help you practice your fundamental theorem of calculus. So we're going to plug in 2. And we're going to subtract the same expression with 1 plugged in. So we have 32 over 3 plus 32 over 5 minus 4/3 minus 1/5. And hopefully we'll be able to put this in an exact form. So looks like our common denominator, well, first of all, we can combine these. So 32 minus 1 is 31 over 5, and 32 minus 4 is 28. So now let's get a common denominator here. So it looks like we have 93 over 15 and 140 over 15. And so adding these together, looks like we get 233 over 15. So our final answer is 233 pi over 15. So there you go. All right. So let's do a problem set here. We'll do one more together before you try one on your own. We're going to find the volume of the solids generated by rotating each area bounded by the sets of equations, or the graphs of the sets of equations about the indicated line. So you see how it says about y equals 1. That means we're rotating about y equals 1. And notice it says it's highly recommended that we graph, but when you're given these problems, as I mentioned in the previous class, you're not going to be given the graphs. You're not going to be shown this graph or this graph or this graph or this graph. You're just going to be expected to figure out in your own mind or with your own graph what you're looking at. So just be aware of that. So let's graph this to see what we're dealing with. So we have the line y equals x. I guess I'll graph that, try blue. So y equals x looks like this. And then we have the line y equals negative x minus 2. So that's in slope-intercept form. In case you forgot what slope-intercept form is, that's y is equal to mx plus b. B tells us the y-intercept. So we have the point negative 2, or 0, negative 2, that is. That's the y-intercept. And the slope is negative 1. So what we can do is we can start from that point we just drew, and then go down 1 and over 1 to get to the next point. And then go down 1 and over 1 to get to the next point, and then we can go backwards going the same direction, and we see we have our line. Okay, so now x equals -2. That's here. And x equals, well, I guess that's all we need for that. So we'll color in that enclosed region. And then we want to rotate about y equals 1. So y equals 1 is this orange line here. And when we rotate, we're going to get the following shape. Our blue line is going to be somewhere up here, and our red line is going to be here. So we're going to get this type of solid. And obviously we can't really sit here and draw some artistic masterpiece of what we're looking at, but we're going to add the volumes of washers. So this is going to be the washer method. So we're going to calculate the area of this cross-section area and then subtract the area of this cross-section area using our washer formula. So the volume is the integral from -2 to -1. And the reason we know -1 is where our enclosed area stops is because obviously we can see that that's where those graphs intersect. So again, the solid is something that's rotated around, so it's hard to see the solid exactly because we'd have to be pretty good artists. This is not an art class. So we're going to find the area of the bigger circles, and the radius of the bigger circles is this distance here. But how do we find that radius? Well, we're going to take this length, which is 1, and then we're going to add this green length. The problem is that green length is a negative number. So if you just add add 1, that pink length, to the green length, which is the y value of the point here, it's not going to represent the length that we're looking for, which is this it's not this yellow distance here. So you have to change the sign of that green length. So it's going to be 1 minus x. Now that's really confusing for students, really confusing. Why are we subtracting x? Well, because when this blue graph is over here, this length is obviously going down. It's going to be a negative number. So we don't want to add a negative number to 1. That's not going to give us this length, and that's the problem. That's what causes so much confusion with this. So again, when we plug in, say, -1.5, for example, we plug it in there, and we have a double negative, so it's 1.5 is actually added to 1 rather than subtracting 1.5 from 1. Again, it's very confusing. So now we're going to subtract the radius of the smaller circles. And the radius of the smaller circles is this radius here, or this length here. So we're going to have to add 1 plus this green length. And again, the green length is negative because it's going down. If we plug in, whatever x value around here to get this length, it's going to be a negative number. So if we just add a negative number to this this pink 1, then it's not going to be the overall length that we're looking for. The length we're looking for is this length here. So believe it or not, the radius is going to be 1 minus, and by the way, we need to multiply by pi. It's going to be 1 minus negative x minus 2 squared. Now, I want to make sure that there's no confusion about these expressions here for the radius of each circle. There's more than one way that you can write this expression, for example. You can write it like this, negative 1 minus x minus 2. That's when you're adding a negative number with another negative number. Now, how do I know that this represents a negative number? Well, because in this region, the red graph is below the x-axis. So if you plug in like negative 1.5 for x, this green expression here is going to be negative. So you have a negative number, a negative green number plus a negative blue number. But you can also do it like this. You can have a positive 1, and then you can subtract the negative numbers so it becomes positive. And so now you're adding two positive numbers. If you do it this blue way or this green way, you'll get the same answer for your integral. Now, why is that? Well, how could you have a positive green number and a negative blue number and get the same answer? Well, it's because you're squaring. See how we're squaring that number? So when you square, the negative becomes positive, so it doesn't matter if it's negative or positive. The only thing that matters is that your expression represents this pink length. If you accidentally take a positive number and then add a negative number, well, that's not going to get you this length. That's actually going to get you a length that's less than 1. And it might be this length here. That's not the length of the radius of the inner circle. If you take this number and make it positive and then add this number, which is a negative, again, it's not going to represent the length that you're looking for. So this number and this number either have to be both negative or they have to be both positive when you add them together. So you just have to make sure that you're finding the right length, and that's the most difficult part of this class. So we can take out pi as usual. You don't have to take it out, but it just makes it easier to do the calculations. And I'm going to perform FOIL. And over here, I'm going to simplify the inside part. Before we expand. Okay, so there we go. So we're just double checking all that. And everything looks good. So the x squareds are going to cancel out, it looks like. And so we're going to have negative 8 minus 8x dx. And let's find the antiderivative. plug in 1. And we'll plug in -2. I'm just going to change the signs because it's too much work otherwise. So when I'm subtracting this expression, I'm changing these signs because it gets kind of tedious constantly writing parentheses. So it looks like we have 4 pi. So again, setting up this problem is the hardest part. Coming up with these radii, the blue and the green radii, that's the hardest part of the problem. It can be very confusing. So I want you to get a picture of these differentiation formulas if you haven't done that yet, and get a picture of the disk and the washer method if you need to refer to those, and get a picture of this problem. We use the disk method there, and a picture of this problem. We use the washer method. And I'm going to leave number 1 in the window for you. And I'm going to give you a grid here. And this problem is going to employ the disk method. You're not going to have to use the washer method, so that's a hint there. So try your best on number 2. These are challenging problems to set up. So, and by the way, because we're using the disk method and not the washer method, your formula is going to be fairly simple. You don't need 2 pi r squared, just 1. So try number 2, and when you come back, we'll do it together. Okay, we're back. So it looks like we have 343 pi over 8. Okay. So if you got that right, excellent. So I want you to get a picture of numbers 1 and 2. Again, this blue expression here is the hardest part of the problem. It's not easy for students to see why exactly that's the radius of each one of these disks. So if you look at this disk here, the radius, which is this length plus this length, is actually root x over 2 plus 3. And you don't really have to show this step if you don't want to, but this just demonstrates that typically the length is the difference between those 2 y values. So get a picture of these problems, and I want you to try number 3. Now I'm going to give you a grid. Okay, so go ahead and try number 3. And when you come back, we'll do it together. Okay, we're back. So our final answer is 29 pi over 42. Okay. So there you go. If you got that answer right, excellent. Okay, so I want you to try one more of these. Again, the difference with these problems is that we're not rotating about the x-axis, we're rotating about a horizontal line other than the x-axis. In this case, it was y equals 1. I'm going to give you a grid, so you have a grid now, and be aware that the hardest part of these problems is figuring out these blue expressions, the radii of the cross-section circles. And for this problem, finding an expression for the radius of the inner disk or possibly the outer disk might be challenging, because down here, for example, this length was difficult to calculate because the y values of the red graph and the blue graph are negative values. So how do you make sure that you're finding the correct length, this green length or this green length? It can be very confusing for students, so try your best. Now, what makes this problem even more difficult is the axis of rotation is going to be below the x-axis. And our y values are also going to be below the x-axis. So you need to be careful when you are calculating the radius of the circles. So just be aware that it's going to be a challenge. So you're going to need differentiation formula number 12, which tells you that the derivative of natural log x is 1 over x. So here we have 3 over x. You're going to have to factor the 3, so you have 3 times 1 over x, and you can see we're going to end up with 3 times natural log x when we find the antiderivative of this expression. But you see here that we have negative values that we're going to be plugging in for x. And remember, when you're trying to use an integral and your antiderivative is a natural log function, and you want to plug in a negative, that's okay to plug in a negative value there. You can just change the negative to a positive number. I didn't mention in previous classes, but I'm mentioning now that oftentimes when you find the antiderivative of this expression, it'll be written with absolute value symbols, because you can just change whatever number you're plugging in there to whatever number you get inside the natural log. You can change it to a positive number. That's okay if you're trying to find the value of the integral. In most cases, you can't have a negative inside a logarithm, but in this case, it's okay. So that's this green information there. So try number 4, and when you come back, we'll do it together. All right, we're back. So if you got that one right, excellent. Okay, so now we're going to find volumes of solids that are rotated about vertical lines. And because they're rotated about vertical lines, for example, here we have a region that is rotated about the y-axis. And because it's rotated about the y-axis, our vertical cross-sections are not going to be circles. I don't know what this shape would look like, but it's not going to be a circle. Our horizontal cross-sections, on the other hand, they're going to be circles, as you can see down here. And it's going to be more convenient to think about the radius in terms of y rather than in terms of x. Now, our r values are going to be technically x values. This distance here is an x value of this point. If we write x, y, this green distance here is going to be this blue x value. But even though it's an x, the length represents an x value of a point on the red curve, we're going to write the x value in terms of y. It's just going to be the easiest way to do this. And so our integrals are going to be in terms of y, and we're going to call them dy integrals. So this ornament dy is used for a number of reasons, but we introduce another reason now, and that is to label the type of variable that we're using, or to show what the variable is that we're using in the integral. It's also important to understand that our limits of integration are going to be y values instead of x values. So let's do a practice problem. We're going to do a problem that employs the disk method. It says find the volume of the solid generated by rotating the area bounded by the graphs of these equations about the y-axis. So we're rotating about a vertical line. So we have an area down here bounded by these graphs, and we're going to rotate about the y-axis. So we get this shape, the three-dimensional shape, and again, we can't figure out the shapes of these cross sections very easily, these vertical cross sections. So we're going to use horizontal cross sections, which are circles. Again, because we rotated about the y-axis, our horizontal cross sections are circles. And the radius of each circle is, well, the radius of this circle, for example, is this length. And that length can be considered an x value, but we're going to write it in terms of y. So let me write the formula for our disk method. So that's the formula. Now, again, our limits of integration are going to be y values. So we're not starting from here and going to 0, because this is negative 8, x equals negative 8. We're actually starting from this y value and going to y equals 0. So that y value is negative 4. So we're going from negative 4 to 0. Again, when we, and by the way, I forgot to write dy, not dx, but dy. So the radius is going to be whatever this length is, this black length here, and again, that can be written in terms of y. It's an x value that can be written in terms of y. So y cubed over 8, and of course the radius has to be squared. So that's it. That's how we find the volume for this particular problem. As you can see, it's not really that difficult. So I'm going to take the pi out of the integral and raise the y to the third over 8 to the second power, so then I get y to the sixth over 64. And I can take the 64, or the 1 over 64 that is, out of the integral. You don't have to take the constants out of the integral, as I've mentioned previously, but it just makes it to where there's less clutter in the integral. And so we have 1/7 times y to the 7th from negative 4 to 0. So 1/7 times 0 to the 7th minus 1/7 times negative 4 to the 7th. And I'm going to move this up a little bit, so we have a little more room. Sorry, my computer's a little slow here. So this is going to be kind of a big number. Negative 4 to the 7th power is 16,384. It's going to be negative, but we have a negative here, so that's a double negative, becomes a positive number. So we're left with 16,384 pi over 64. But and I forgot the 7 down there. So we're going to have to multiply 64 times 7. And that's going to be 448. So this is going to be a difficult thing to divide, but I'm going to try dividing by 8. And that reduces significantly. Maybe I'll try dividing by 8 again. And I get 256 over 7. So, looks like that's our answer. You can't divide anymore without getting a irrational or a decimal that is an approximation, so there you go. So let's try another one of these. Notice that if you integrate from a smaller number to a bigger number, then you get a positive volume. If you integrated from a bigger number to a smaller number, then you get a negative volume. Okay, so let's try this problem. Find the volume of the solid generated by rotating the area bounded by the graphs of those equations and the on the y-axis about the line x equals 5. So we have this area bounded by those graphs, and we're going to rotate about the line x equals 5, and so we get this shape here. And so we're going to have to use the washer method because we rotated about a vertical line. So let's see if I can find a color that will help us understand what's going on here. So we're going to find the area of these circles, and then we're going to subtract the area of the inner circle, and that's going to give us the cross-sectional area of a washer. So this area minus this area gives us some sort of a washer. But again, if we try to find cross sections of the solid that are vertical, then you're going to see that it's going to give us a weird shape. It's not going to be a circle. And I know that students will typically try to figure out what that shape would look like if we cut vertically, but that's not easy to figure out. So the formula that we're going to use is pi r1 squared, the integral from a to b of pi r1 squared minus pi r2 squared dy. Again, when our cross sections are horizontal, we're going to use an integral in terms of y. So we're integrating from y equals 1 to y equals 3. Again, these limits of integration, these blue limits of integration, are y values, not x values. And so the area of the bigger circles, that's pretty easy. The radius is going to be constant. It's just going to be 5. And we're going to subtract, so the bigger circles, they're going to remain constant. They're not really changing as y goes from 1 to 3. But you can see that the area of the smaller circles, that's going to change as we go up. See, circles are going to get bigger and bigger. And so what is the radius of the smaller circles? Well, that is going to be 5 minus 4 over y squared. So 5 is this dark purple distance, that's 5, and then we're going to subtract this green length, which is 4 over y squared. 4 over y squared is an x value. It's not exactly obvious that that's that blue distance, but it's going to be 5 minus 4 over y squared. So there you go, there's the integral. So again, not exactly something that is easy. It takes a lot of thought to understand that. Now again, this green expression here, that is the distance. That's an x value. That's the distance from the y-axis to that red graph. Again, it's just easier to write our expressions in terms of y. So now we're ready to see if we can calculate this. We can pull pi out. You don't have to pull it out, but it's easier to write if you pull it out. Looks like we're going to get 25 plus 40 over y squared minus 16 over y to the 4th dy. So let's double check that. I think that's correct. So good thing those 25s cancel out. It makes it easier. And we can write those fractions in exponential form, now that I think about it. And I'm going to find the antiderivative. And actually that's going to be a 3 now that I think about it. Okay, so let's double check all that, make sure we did it correctly. Everything looks right. But we don't know how to analyze these expressions like this, so we're going to change to negative 40 over y plus 16 over 3y cubed so now let's transfer to the next page because we're out of room. Okay. So we have negative 40 over 3 plus 16 over 3 times 3 cubed plus 40 over 1 minus 16 over 3 times 1 cubed. So it looks like we're going to have 16 over 3 and negative 40 over 3, so that's going to be negative 56 over 3. And looks like we're going to have 16 over 81, and so on and so forth. So we can combine this. I know it's kind of a hassle, but it's better to write an exact answer if you can. So it looks like we're going to get negative 1,496 over 81 plus 40 all times pi. And that's going to end up being 1,744 pi over 81. So there you go. Okay. So that was the shell method with a dy integral. Again, our cross sections are horizontal rather than vertical. So let's try one more of these together. It says, find the volume of the solid generated by rotating the area bounded by the graphs of each set of equations about the indicated line. So the indicated line would be x equals -4 in this case. So again, notice it's a vertical line, so we have to use a dy integral. Now over here, notice that it's kind of strange because usually we're used to seeing y equals e to the x. We know how to graph that. That looks something like this, right? But what if we switch the variables? Well, if we switch the variables, we take this graph, we reflect it about the y-axis, which gives us the green graph, and then we rotate 90 degrees clockwise, which gives us the purple graph. So we want the purple graph. That gives you an idea of what that should look like. But we need to be more precise, so I'm going to plug in 0 for y, and we get 1 for x. We can plug in 1 for y, and we get whatever e to the 1 is, and you can look on your calculator for that. That's going to be 2.718. That's going to be about there. And if we have 2 for y, x is going to be 7.389. And that's probably good enough to get a rough graph there. Okay, now we need to draw y equals 0. That's that green graph. And y equals 2. That's here. And now we need to graph x equals -y minus 2. So remember, we only need 2 points to graph a line. So let's plug in 0 for y, and we get -2 for x. So that's that point there. And let's plug in 2 for y, and we get -4 for x. So 2 for y and -4 for x would take us to about there. So it looks like our graph looks something like this. All right. So what area are we talking about here? Looks like it's going to be this area. That's the area that we're enclosing, the area bounded by those graphs. Actually, not that other part, just the upper part here. And if we rotate about that line, x equals -4, I don't know if we're going to be able to fit this on the page. Probably not, but it's going to be somewhere over here. It's going to look something like that. So the we're going to cut across like this. We're going to have horizontal cross sections, and they're going to be circles. That's the bigger circle, and this is going to be the smaller circle. So what is the radius of a bigger circle? Well, that's going to be the distance from here all the way to there. So that's our task, is to try to figure out an expression for that. So volume is going to be the integral from y equals 0 to y equals 2 of pi r squared, and we need to figure out r. So again, what is the distance from here to here? Well, that's going to be 1, 2, 3, 4 plus whatever this distance is. This light green distance. What is that distance? I probably should use a different color. This light blue distance. Well, that's an x value, the x value of this point. But that x value can be written in terms of y. And that's this expression here. So again, we have 4 plus e to the y. Now the reason that we don't subtract e to the y, as we did in some other problems, is because this value is going to be positive. So that's what we want. We're adding two positive numbers. Even though this line is written as x equals -4, I'm just putting a positive 4. If you wanted a -4, then we'd have to subtract e to the y. That would give us the same answer because we're squaring. Okay, so now the inner circles, they have a radius that's equal to this distance. What in the world would that be? Well, that's going to be 5 minus whatever the x value of this graph is, and that x value is going to be -y minus 2. So that is not easy to figure out. Not easy at all. So these problems can be a little challenging. So, and actually that should be 4, not 5. So 4 minus this number, and now I think about it, I think we should be subtracting, or actually we should be adding that number. So we need this to be a plus sign, because again, we want to take this distance and subtract this distance, where we're going to be taking away these values. So again, this is where things get really, really difficult to think about. This value, this blue value here, is 4, but then you're going to add this negative value, which is going to take away from that blue value, and then you're going to be left with this pink length here, which is what we want. That's the radius of the inner circles. Again, not something that is very obvious. So I'm going to pull pi out, and I'm going to FOIL this. And looks like we're going to have 2 minus y squared. to subtract. I'm going to FOIL that and subtract. And let's combine like terms if there are any like terms. So 16 minus 4 is 12. And doesn't look like there's any other like terms. So now we can integrate. Now this is a U substitution, but it's such an easy U substitution that again you don't really have to show. You can probably do it in your head. So let's double check all that. Everything looks right. So now we're going to plug in, we're going to plug in 2. So the y values go from 0 to 2. Again, these limits of integration, very important to understand. The limits of integration are y values, not x values. And then we're going to subtract the same expression with 0 plugged in. So there we go. Let's simplify. And let's make sure we did all this correctly. Remember, anything raised to the 0 power is just 1. So we have 24 plus 8 minus 8. So it looks like these 8s cancel out. We can combine these green fractions. Negative 19 over 6. We have our 24. And it's probably best just to do the rest on our calculators. So I'm entering this into my calculator. It's probably going to take a while because there's a lot of stuff to enter in. But if you know how to use your calculator, it's not so difficult. So I get 336 approximately. 336.9196. I guess we can just round that off to 92. Okay. So there's just one more example of a dy integral. So I want you to try number 6, but before you do that, I want you to get a picture of these problems here, or this one problem, and then this next problem here. And I'm going to leave number 5 in the window, and I want you to try number 6. So going to attempt number 6. Number 6 is going to be the disk method. And because you're rotating about the y-axis, a vertical line, you're going to write a dy integral. So attempt number 6, and again, your limits of integration are going to be y values. Now, you see here we have x equals y squared. We know how to graph y equals x squared, but how do we graph x equals y squared? Well, you're just switching the letters. When you switch the letters, what you do is you graph the graph that you're familiar with. That's y equals x squared, roughly. And what you do is you reflect about the y-axis, which is not going to change it. Then you rotate 90 degrees clockwise, and that's roughly what your graph is going to look like. So try number 6. When you come back, we'll do it together. Okay, we're back. So if you got that number, excellent. So I want you to take a picture of these true problems here, and they will help you do number 7. So I want you to try number 7. Be aware that we're using these green equations to enclose our area, but these equations are not the limits of integration. Remember, the limits have to be y values, so please don't make that mistake. So what are the y values? Well, you're not going to know until you graph. So you're going to have to graph this. So try number 7, graph everything, and then you're going to rotate the enclosed area about the line x equals 1. When you come back, we'll do it together. Okay, we're back. Okay, so have you got that right? Excellent. All right. I want you to try number 8. Now notice this expression here, it's not going to be exactly obvious what that is. If you square both sides and divide by 2, you can see it's actually going to be a parabola. But because we don't have a plus or minus symbol, we don't have a plus or minus symbol in front of this root, that means that only one side of the parabola is going to be graphed, and it's the side where x is equal to a positive number. So go ahead and try number 8. When you come back, we'll do it together. Okay, we're back. So if you got that answer, excellent. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1, and screenshot number 2, and screenshot number 3, and number 4, and number 5, and number 6, and number 7, and number 8, and number 9, and number 10. But don't go before you get your homework. Remember, the homework is not optional. It must be done correctly and completely and kept in order in your binder. So here's screenshot number 1 of the homework assignment. And screenshot number 2. Notice I've provided graphing paper for you. Here's screenshot number 3. And so that's the homework, but don't go before you get the answers. Remember, it's not enough just to attempt the homework, it must be done correctly. So if you get a wrong answer, figure out what you did wrong and fix it, or else you haven't done the homework. So here's the answers. Sometimes you can write the exact answer, but other times you cannot. For example, number 1. You could write the exact answer for number 1, but it's okay to write it as a decimal. But most of these you can write as a factor of pi. But you can write either, a multiple of pi. You can write them as multiples of pi or decimals. So anyway, get that homework done, and I'll look forward to seeing you in the next class.